can't share my screen. There we go. So, okay. So a quick comment regarding the mid-semester check. I sent you a note about that, and I saw some of you already started filling that. It's just few questions to see how you guys are doing, what we can do to help you learn and answer any concerns so that it's not too late in the semester. So thank you for those of you that already filled it out. And if some of you still did not see it, please go in just as an encouragement +2 on filling that. It's just extra credit. You don't have an obligation, but I just want to incentivize it a little bit. So please do fill it. I already saw a few comments and I appreciated them a lot. I know we had issues with the quiz one. It's the first time we do virtual, so we were all, it's a learning experience to all of us, and I'll take that into consideration for next time we have a quiz. And I just want you not to worry too much about it. It's not the end of the world. It's equivalent to a lab report. It's like 30 points equivalent to a lab report, and you're doing well in lab reports, so that will counter anything. And if you do well in the next quiz and the midterm and the final, trust me, and then you have lots of extra credit. I won't worry about it at all if I were you. So that's with regard to the quiz one. And also I saw some comments about the class being tough. Yes, I mean, I can't deny that it is tough, just because not I want it to be tough. It is the nature of the class being a lecture component, a lab component, and a writing intensive component. And we're trying to balance all of that in one class. But I understand it's a lot of work, and I appreciate that you find that it's a lot of work. But I come to me for any help you need, any specifics. And I know we have 2 lab reports that are full lab reports in a row, but you get a break after that. You get 2 lab reports that are partial, and then for approximate analysis lab report, you get 2 weeks to write that. So you'll have more time. So, and we only have 4 full lab reports the entire semester. Trust me, when I started teaching this class, we had 12 full lab reports. So I did take into consideration students' comments and modified the class and made it more manageable each year. So your comments are very important. So please do keep them coming, and I will read through all of them, and I'll do my best to address as many of them as I can. The other comment that actually multiple people said the same thing, and it's about material that you want more time spent on questions and answering. Please do stop me if you feel that I'm rushing. I don't really care about finishing a lot of material as much as I care about you getting the material that I'm covering. So I know that the medium is different this year for everybody. For me, I'm not a tech person, so I had to learn a lot too. So it's not really easy to communicate when half of you are online and the other half is here. So it's difficult. But feel free to just raise your hand or even unmute yourself if you're watching. Just tell me, Pian, can you repeat? Or I have a question. I would never criticize a question. Just to let you know, I think any question is a legitimate question. There's no stupid question in my agenda. So that word stupid, I hate it. My daughter, since she was little, I said stupid is a bad word. Do not use it. When she was 12, she goes, Mom, everybody says stupid. So anyway, I don't like that word. There is no stupid question, no dumb question. Every question is valid, and I respect that. So please don't feel shy asking any question. So interrupt me for questions. And sometimes if I forget repeating a question in class, it's okay to remind me again in the chat box. And we have Brigitte, we have Rachel, we have other TAs that would stop me and say, can you please repeat the question that was asked in class. Because I'm in the mode of teaching, I don't necessarily keep up with everything around me. So remind me, it's okay. It's okay to remind. And keep those comments coming. I'll try to address as many of them. This is very essential. I want you to learn and I want you to enjoy this class. You might not appreciate it now because it's a lot of work, but at the end of it, you might look back and say, oh, what? I learned something out of this class. So bear with me and hopefully it will be a good experience. All right, so we're jumping into another very essential topic in food analysis. What we covered so far, our introductory chapters, were just introductory about the importance of food analysis, how we sample, how we do data analysis, what's about nutrition labeling. But then we dived into chromatography, and now we're going to enter spectroscopy. The reason we're diving into these harder topics first is because later on, in almost every chapter, we need spectroscopy to analyze, we need chromatography to separate and then quantitate. So it's very important for us to understand the principles of these major components of analysis, chromatography and spectroscopy, before we move on to analysis of components. You might find the next half of the semester easier because you covered the hard part. You covered the hardcore and then you would do more applied type of work. So spectroscopy, can anybody define what spectroscopy is? So those of you online, you can chat. I can open the chat box here to see answers, and those here can raise your hand as well. So how do you define spectroscopy? What is it about, really? Very simple, few words. Sam, go ahead. Okay, so there are some words in your statement that are very correct. Light, reflected, type of wavelength, very good. But can we pinpoint a definition as it relates to food analysis? Let's see. Okay, that is analyzing components with light. That's very good. We're getting really close here with all the terms. Let's put them together. It's the interaction of a species, a matter, with light. And utilizing this interaction to do quantitative, qualitative type of analysis. So it's very simple, interacting light with matter. And in this case, food species, molecules, atoms, different components. Okay, so let's look at that. Here is a question for you. The following is associated with a light wave. When you hear the light wave, what does it mean to you? So you have different components. Which of these components are associated with a light wave? Georgino? All of the above, yes. So you can characterize light as a wave made up of electric field and magnetic field. And also, you can think of a wave as pockets of energy. And these pockets of energy are called photons, photons of light. They're pockets of energy. So you can think of them as an electric magnetic field wave or photons, light photons. So all of the above. Following spectroscopy as means of analysis, detection can be based on. If we use spectroscopy, the question is asking, if we use spectroscopy, how do we detect our species, whether it's molecules or atoms? How do we detect them? By absorption of a photon of light, by emission of a photon of light, or by dissipation of heat? Give a guess. Give a wild guess. Don? Huh? A and B. Yes, correct. It's A and B, Don. Why? Because although there is a form of dissipation of heat, you know, wherever there is an atom or a molecule, when it absorbs light, it's going to go to an excited state. And it won't stay there. It needs to go back to ground state. Oftentimes it goes back by dissipation of heat. Sometimes it dissipates a little bit of heat and then emits a photon that we can measure. That's fluorescence. But if it's only dissipating heat when it's going down, that heat is very, very small amount. We cannot detect it or measure it. So therefore, although it happens during spectroscopy, dissipation of heat happens because we're going down to the ground state, it does not count towards detection. Okay, so we need to learn terms because you're going to hear a lot of these terms in the next 3-4 lectures. So what does that mean to you? We already defined spectroscopy, a study of interaction of material and light. So there's the material or the matter. So the matter, you have two species. You can detect molecules or you can detect atoms. So some of you already did the atomic absorption lab. You were detecting absorption of light by atom in the gaseous state. But many of other examples of detection is for molecules. So we have the species. Are we detecting molecules or are we detecting atoms? So that can impact the type of spectroscopy we study. Then you have the radiation matter interaction. There has to be an interaction. The matter has to absorb the light in order, not necessarily absorb. We have absorption. We can measure absorption. Some species emit light as they're going down to their ground state so that we are measuring emission or fluorescence. Sometimes we measure neither. We measure light scattering. So the matter is scattering light and we measure that. Sometimes we're using light for diffraction. So we will give examples of diffraction of light, scattering of light, absorption of light, emission of light, or light interference, or refraction of light, like the refractive index measurement is based on the refraction of light. And then there is an important component, which is the electromagnetic region. That means which region we are measuring absorption at or fluorescence. So in fluid analysis, you have really three main regions. So you have the UV, the visible, and the infrared. So these are the three regions that are of interest or are applied in analysis, or for the analysis specifically. So how do they differ, all these regions? They really differ in the wavelength. So this is the wavelength, lambda. And then you have, starts with very small and it goes bigger as we go down in this region. The wavelengths become bigger. Now, the energy associated with the wavelength, it is inversely proportional to the wavelength. The shorter the wavelength, the higher amount of energy that wave carries. The longer the wavelength, the less amount of energy that wave carries. And it will make sense in a minute when I show you the wave and what it looks like. Okay, but what you really need to know is our region, the UV visible infrared region. You want to remember another thing, the higher the wavelength, the lower the energy, and the opposite is true. Okay, so in spectroscopy, we have UV visible absorption. So either we have chromophores that absorb UV light and chromophores that absorb visible light. So we can measure absorption. We can measure absorption of infrared for IR instrumentation, mid-IR or near IR, and we'll cover that in the IR section. We can measure fluorescence. which you have to absorb. It's not you, but the element, the molecule has to absorb light in order for it to emit light. So there is absorption, but we are detecting the fluorescence or the emission of light. So there is atomic absorption, which is a very unique component of spectroscopy, and we have different types of atomic absorption. We'll talk about that on Friday. And we have the inductively coupled plasma emission spectroscopy. So that's also we use it for measurement of elements in the atomic state. We have the nuclear magnetic resonance, which is NMR. You have about a chapter in the book, but I'm not covering it during the semester. Honestly, you need a semester long to understand NMR. So it is there. It's part of spectroscopy, but it's a different field of spectroscopy. Mass spectrometry has nothing to do with interaction with the light. The commonality between spectroscopy and spectrometry, you have spectra, you generate spectra. One spectra is based on absorption of light or emission of light, and another spectra is based on the ions that are detected in a magnetic field. And Gary talked about mass spectrometry, so you know what it is about. It has nothing to do with interactions of light in particular. Okay. Moving on. Remember to interrupt me if you have questions. Okay, so applications. There are so many applications for spectroscopy and analysis. Can you think of categories of applications? Where do we utilize spectroscopy and why is it needed, or when is it needed? For what reason? Don't go specific, just categories. Sam? For nutrition labeling?
Yeah.
Okay, yeah, compositional analysis. Yes, we need spectroscopy for compositional analysis. Very good. What other applications do we need it for? Gene? Huh? Adulteration, detection of adulteration, food forensics. Yes, we look for adulterants by looking at IR spectroscopy, for example, to kind of differentiate a product with an adulterant and a product without an adulterant, and how would the spectra look like. All right, that's very good. So we talked about compositional analysis, we talked about adulteration. What else? Like, what did we exercise in HPLC when we looked at the spectra from the PDA? When we were looking at caffeine, what were we trying to do? Looking at the spectra and trying to do what? Toxicity, detect impurity. What were we doing? We were measuring caffeine, yes? What did we use the spectra for? Yes, Anastasia? What's that? To get the wavelength at maximum absorption. Yeah, so basically what we were trying to do is identify our peaks. Which one is caffeine? So we use the spectra for identification, right? So we use the absorption and emission data. The way the absorption data, we measure it area under the curve. So what do you do with that? We do it for quantification, general quantification, whether for food composition or not necessarily for nutrition labeling. Any quantification we want to do, we need to be able to quantitate using a value, and that value is the absorption and measured by area under the curve. So we said quantification, detection, adulteration, food forensics. Let's see what else I have there. So we have qualitative detection. We talked about that, which can also be the identification piece too. So we are detecting, we are identifying, and then we're quantitating, and specifically this is applied for compositional analysis. But we do quantitate other components that don't necessarily go on your label, like quantitating polyphenols, looking at antioxidants. That doesn't go on the label. Okay, quality assurance and forensics, looking for adulteration. Structural elucidation. What do we know about the structure? If there is an unknown, we can take the spectra and try to figure out, especially IR can give us very good structural elucidation because IR can give you the vibration and stretching of specific bonds so that you can piece things together and try to get some structural information. Okay, so these are recap questions. I'll bring them back on Friday, but they're there for review. Okay, light. So let's try to remember the physics. I'm not a fan of physics, but I enjoyed the light component of physics when I learned physics. So, some basic information on light and wave. So light, we can characterize it as wave-like properties or as pockets of energy properties, like photons of light. So just to remember what the wave is about, it's a combination of electric field and the magnetic field. So, and then other things that you want to remember about the wave is that you have oscillations. So you have a maxima and you have a minima. And then the magnitude here from the baseline to the maximum point is called amplitude. Okay, and then these oscillations, every oscillation is one wavelength. So from the height of the maximum here to the height of the successive maximum, the one that comes next to it or after it, the distance in between them is the wavelength. You can relate that now to energy and the length of wavelength. The more oscillations you have within a unit space of space, the higher the energy. So the more you have oscillations within a unit of space, the more the energy. And that's why the shorter the wavelength, that means the higher is the energy because you have more oscillations within a period of time or an area. So, and you can say number of oscillations or you can call it frequency. I don't know why it should have a frequency symbol, just like looks like a V. I don't know why it looks like a question mark here. But the frequency symbol is that V-like symbol, which is the number of occurrences of a repeated event, which is the oscillation that you see per time unit. The more of that, the more energy you have. And the amplitude, like I said, is the magnitude. So it's correlated with the height of at the maximum point. So like here, from here to here, that's your amplitude. Okay, so when we think of light with wave-like properties, we think of interference, diffraction, and refraction of light. So interference is very important when we cover IR spectroscopy and talk about the instruments of IR. So in interference, so in the instruments of IR, they can work with interference of the wavelengths to either increase or amplify a certain wavelength or reduce the intensity of certain wavelengths. So the way it's done is how the wavelengths meet in space. So if two wavelengths or two waves, not length, if two waves, different waves, met in space and their minima and maxima overlap in time. So they meet at the same time where their maxima and minima meet, overlap. We get amplification. So the magnitude increases. So we get amplification. If they meet in space in opposite way. So their the maxima of one wavelength meets the minimum of another wavelength. So the maxima of one wavelength, let me go here, this is a maxima of one wavelength meeting the minimum of another wavelength. They kind of cancel each other, especially if they have similar magnitudes. So if similar magnitudes and they meet the opposite way, then they cancel each other. So between 100% amplification and 100% cancellation, there are so many different scenarios in between. And IR instruments are built in certain ways with mirrors that reflect light in certain ways to get an amplification or a cancellation. And we'll talk more about that when we cover IR. Okay. Now, diffraction of light is very important in quantitative spectroscopy. Why? Because when we want to quantitate, we need to do that at monochromatic light. And I'll talk more about monochromatic light in a minute. But what happens is you have your incident beam, you have your source of light, your lamp, and that light is going to hit a diffracting grating system. So a grating system that will diffract the light. What does that mean? Break it into its individual components. The individual components of the light, we have multiple wavelengths at different, with different wavelengths, basically. Multiple waves with different wavelengths. So I'm breaking light that is made up of so many different waves with so many different wavelengths. I'm breaking them into monochromatic waves. So this is important. We'll come to that. Refraction of light, an application that is very common is the refractive index, where you measure total soluble solids. It's a way to measure total soluble solid based on differences in the angle of incidence of the beam. So in one medium, let's say air versus water, or if your water now has 1% solids or 5% solids or whatever, the refraction index will differ based on what's in that other medium. So the bending or the changing of the angle, because you have that we call refraction of the light. When it goes from one medium to the other, it refracts. It's change in the angle of incidence. Okay, great. This is all basic physics reminder of things. So the particulate properties of light, we call it the photon. So that's the pockets of energy there. So a wave consists of pockets of energy. So every oscillation carries a specific amount of energy. So we have pockets of energy moving along in the wave. So the energy of the photon can be defined in terms of the frequency of the wave. And the frequency of the wave is that V-shaped symbol. So energy equals H, which is a Planck's constant. It's just a constant. And then you have the frequency. Frequency, how many oscillations I have per unit time. Okay. So what is a monochromatic light? From the name, we have a color, okay? Mono, it means I have a singular wavelength. I have light with a singular wavelength. So all of the waves in this light have a singular wavelength. So it's electromagnetic radiation composed of waves having a single frequency and wavelength. So same amount of oscillations and the same wavelength. So why is it important? We will learn about that when we talk about Beers-Lambert law later on in a couple of lectures, which is very important for quantification. To abide by Beers-Lambert law, you need to do quantification at the singular wavelength. So it's very important to diffract the light or the source of light into singular wavelength and then select one for quantification. For structural elucidation, you do not have to select one. The more waves you have, the more identity you can get based on the absorption of your molecule. But for quantification, a monochromatic light is essential. So with that, in order to get you a monochromatic light, you need a monochromator. So that means a unit, something that would give us, break that light into singular wavelength light. So that's what we call monochromator. So what it is basically a unit in your spectrophotometer or spectrophotometer. So what it is, it's your light, your source of light. Here's your incident beam. It's hitting a mirror. Usually you have mirrors because you are confined to a small space. So you kind of direct the light in mirrors to keep everything contained in a small space. And then the light hits the mirror and gets reflected. Okay, so the light gets reflected onto a grating system. So in that incident beam right now, when it hit the grating system, it gets diffracted into multiple wavelengths or multiple waves with multiple wavelengths. So these waves, we have to select the wavelength we want, like when we selected for caffeine to 72 nanometer. So when we select, there is a unit there that will allow the passage of a very well-defined wavelength. So it can move in whatever direction we want to select for the light that we want, to select for the wavelength that we want. So it helps us select the monochromatic light that gets projected onto a mirror, and then that light gets reflected to our sample, where the sample compartment is. So it gets reflected, and whatever components in the samples that absorb at that one wavelength would be absorbed, and you collect data, would absorb the light and you collect the data. So you can either have a grading system like this, or you can have a prism where the prism kind of disperses the light as well into individual wavelengths. So photon flux and brightness. You can hear photon flux, you might hear brightness or radiant intensity, but if you hear photon flux, for example, it's the number of photons that are flowing across a space, a unit area, per unit time, per second, for example. So how many photons are hitting a surface perpendicular to the light, a particular surface per unit time? So we can refer to that as brightness or radiant intensity. So you can increase the radiant intensity of your light source, then you can enhance sensitivity and detection. So it is a measure of, the intensity is a measure of the energy, the frequency, how much photons of light really are hitting my area. So the A is for the area per unit time. Okay. So going back to the wavelength, again, this is just a reminder, and this is actually showing you, so the oscillations and the wavelength when it is short, so that you have higher frequency, so that means higher energy. And then as it gets longer, you will get lower frequency and then lower energy as it gets longer. So we have, remember, opposite relationship between wavelength and energy. So when we want to talk about absorption and emission, so it's not refraction or diffraction or amplification or cancellation or reflection of light. When we talk about these terms, we talk about it in terms of wavelength properties. But when we want to understand absorption and emission, we talk about it as photon properties, so, or particulate properties. So when we think about it as particulate properties, as photons, here's what happens when an atom within a molecule, it can be a singular atom or an atom within a molecule. It could be an electron in the valence shell or the valence electron, the outer shell, or it could be the electrons in a bond between two atoms. So what happens is when the light hits the atom or the molecule, the valence electron will jump to a higher level or a higher shell. So this reaches an excited state. So the electron absorbed the energy that was projected onto it. Same amount of energy. So whatever is the energy that hit it, it absorbed it and went to the excited state. Now it won't stay there. It will go down back to ground state. And in that case, in this case, either it just emits heat and done, we don't measure that, or if it's a fluorescent, it would emit energy. However, the energy emitted is of a longer wavelength. Why? Because part of the energy it absorbed, it gave out a heat. So now it has less energy in that emitted photon. Okay, so the wavelength of absorption is always lower than the wavelength of emission. So when we're doing spectroscopy and we're measuring fluorescent, there's always, when you go set up your equipment, set up your fluorescent spectrophotometer, you always set your absorption wavelength and you set your fluorescence wavelength. They're two different wavelengths. One has shorter wavelength, which is the absorption wavelength, and the other one has longer wavelength, which is the fluorescence wavelength. So whenever you work with that, remember, oh yeah, I learned this somewhere. Absorption wavelength is different than the emission, and the emission has longer wavelength and lower energy. Okay. So this is just, it kind of cement what I said in terms of the molecule or the atom going from a ground state to excited state. And the difference is the frequency multiplied by that. Difference in energy is the frequency. Again, I don't know why I have a question mark, but it is this here, the frequency. Well, let me point by that. Here's your frequency. The question mark here is supposed to be frequency. So it's the difference in energy between ground state and excited state, which is directly related to the frequency of the light that was absorbed. So the molecule increases by an equal amount of energy that hits it. So whatever is the energy that hit that molecule or atom, the amount of energy absorbed is equivalent to that energy that hit it. However, one important thing that will help you understand why every molecule, for example, or atom, they have a different spectra. So different molecules absorb at different wavelengths. They have different lambda maxes. Why is that? Because within each molecule or atom, you have electrons and you have specific allowable energy. That means it's not continuous. It's not 1, 1.2, 1.3, whatever the continuous scale is in terms of energy for all the atoms and all the molecules. No. Every molecule, every atom, all the electrons in the different bonds, they have different allowable energy. So if the wavelength carries the allowable energy for that molecule, it will absorb it. If it carries not allowable energy, it won't absorb. So that explains why some molecules absorb at particular wavelengths and others don't, because of their allowable energy scale. Every atom has its own allowable energy scale. So it is discrete steps. That's what that means. Allowable energy scale, or you call it discrete steps, and it's not a continuous system. Okay. So we have different energy levels. A molecule would have different sets of energy levels. So it has the electronic energy level, it has the vibrational energy level, and it has the rotational energy level. However, an atom has only an electronic because there's no bonds within the atom, right? So there's no vibration of the bond. And of course, there's no rotation because in a molecule you have center of gravity and the molecule rotates around its center of gravity. So an atom carries only electronic energy pockets. So here you can see if it is an atom, you don't see vibrational pockets or rotational pockets. You just see levels of electronic energy, E0, E1, E2. So all you see for an atom. For a molecule, you see different energy levels because a molecule have atoms that have electrons that can get excited, so it has electronic levels, energy levels. And then a molecule have bonds, so they stretch, they vibrate. So you do have vibrational energy pockets within, and they're usually smaller energy pockets. So, and the wavelength or the region in the magnetic spectrum is IR, infrared, for the vibration. And infrared has longer wavelengths than UV and visible. So it is of smaller energy and hence the smaller vibrational sections that you see. Rotation, it's even larger wavelengths, microwave wavelengths. It's even larger, so it carries less energy. So that also is less smaller pockets of energy for the rotation than the vibration. Does that make sense? So we have three forms of energy: electronic, vibrational, rotational. And the electronic carries the highest energy, so it has the highest allowable pockets of energy, whereas the vibrational are of a smaller energy, higher wavelength excitation by IR, whereas the excitation of electronic energy is by UV invisible light. This is basically what I explained. This is just another kind of detailed explanation about the electrons in different orbits. They carry different potential energy. They can be excited at different wavelengths. That's why you see a molecule or an atom might be excited at different wavelengths. Based on the wavelength and the energy it carries, different electrons get excited within the allowable pockets of excitation. That's why we see a spectra that is different for every atom and every molecule. So when the energy of the electron changes, it's definitely will the energy of the entire atom and the energy of the entire molecule if the atom is within the molecule. That's what this is saying right here. Changing the potential energy of an electron will lead to a change in the potential energy of the atom, and if it's within a molecule, then within a molecule. This is explaining the electronic energy, and it's stating, like I said earlier, that it is within the UV vis region of the magnetic spectrum, of the electromagnetic spectrum. So that's exactly what I said earlier, is within that region, the UV visible region, we have only electronic energy, and the atom or molecule changes levels of energy in the electronic states. And this talks about vibrational energy, which is energy of the bonds. So it's only in molecules, not in atoms, where you have bonds that can absorb in the IR region. Okay, so the IR region carries the energy that is equivalent to the allowable vibrational energy within a molecule. And last is and I said that in the IR region. And then last is the rotational. And I said this is rotation in a molecule, again, not an atom, around its center of gravity. And this is in microwave spectroscopy, so microwave region of the electromagnetic region, where you have longer wavelengths, so you have less energy, so the rotational pockets are smaller. But we don't apply microwave spectroscopy in food analysis, so don't worry about it. So you'll see UV visible, which is electronic energy. You'll see IR, which is vibrational energy. That's the main application in food science or food analysis. So here is just a summary of what I said, is that you will only see the electronic regions. You won't see within an atom any pockets for rotational or vibrational. So it will be empty, just E0, E1, E3, etc. For a molecule, you have all the possibilities. The molecules can be excited by electronic energy, vibrational energy, as well as rotational energy. This is what I said earlier, is this knowledge is what explains to you why each molecule or each atom have a different spectra or absorb at different wavelengths, and gives you this power of identification. Unless two molecules share a chromophore, they have the same chromophore, but they differ in different structural components, we cannot tell the difference. But if they differ in the chromophore, then we can see very well, in this example, the difference in spectra of this component or this compound versus the other compound. So a different wavelength, no matter, it doesn't mean that one molecule only absorb at high wavelength and one molecule only absorb at low wavelength. That has nothing to do with the amount of energy. What it has to do is with the distinct regions that are allowable for each molecule. So each molecule will have allowable pockets of energy, and it could be low energy, it could be high energy. It doesn't matter. It doesn't go that way. So that's why we see some molecules don't absorb light at high energy, like at a wavelength of 240 or whatever here. And then at lower energy or higher wavelength, it doesn't absorb that much. And then it absorbs again at even lower energy or higher wavelength. So it has nothing to do with the actual amount of energy. It has to do with what's allowable within each molecule. So that's why it's very important methods of analysis for detection, for identification, for structure elucidation, especially IR, more than UV and visible light. Because with IR, you can see the stretching and bending of different types of bonds within the molecule. So it tells you a lot more about the structure. So last slide here is just, again, what I said about emission spectroscopy. It's also not all molecules can emit light, or all atoms can emit light. Some fluoresce, some don't fluoresce, and some fluoresce that in a way that is not very detectable. So some select molecules can fluoresce, and sometimes the fluorescence gives you much more better sensitivity than the absorption of light. So, but some molecules don't, they just dissipate heat, and that cannot be measured. So just as a reminder that emission of light is basically you have to absorb the light first. So the molecule has to absorb the light first. It absorbs the energy, and as it's going down to the ground state, it emits some heat and the rest as a wavelength or as a photon of light that we can measure. Okay? And longer wavelength has lower energy. That's what I want you to remember from this. That's all for introducing spectroscopy. On Friday, I'm going to cover atomic absorption. And next week, we'll talk about UV, visible spectroscopy, and IR before ending the spectroscopy section. Thank you, guys. I'll see you on Friday.